Hello there, and welcome back. In this video, we're going to continue our exploration of continuous random variables and probability density functions. In the last video, we discussed continuous uniform random variables and pretty much how you can calculate probabilities, expected values, variances, percentiles, and several other things just based on a generic probability density function. So remember, for a continuous uniform probability density function and a continuous uniform random variable, we usually assume the likelihood that any event in some continuous interval is equally likely. So let's assume we're on the continuous interval a to b, and if that is the case, that means the length of this interval is going to be b over a. So if this is a uniform distribution, then the likelihood of all the values in between those numbers a and b, exclusively or not, must be equally likely. And in order for this to be a continuous distribution, then the area underneath this curve, so the integral from a to b of this density function fx of x, must be equal to 1. Since this is a rectangle, the length and the width must be reciprocals of each other. That means the height of this distribution must be 1 divided by b minus a. And then we can calculate probabilities on this. For example, what is the probability that a randomly selected value between a and b lies between some other two numbers, for example 3 and 4? We'll just simply find the area of this little box here, and that would give us the probability, right? So that is the probability that x lies in between 3 and 4. So also keep in mind that for the continuous spectrum, the probability that x is greater than 4 and the probability that x is greater than or equal to 4 are equal to each other in the infinitesimal sense, because the probability that you're exactly equal to 4 for a continuous random variable is infinitesimally close to 0. So therefore, even though these are different problems, they do represent different things. But they are equal to the same number. So that's a very important thing to understand about continuous random variables. So now we're going to introduce two more special probability density functions, the exponential and the gamma distribution, that are often seen in applications in the real world. So let's just lay down the foundations of what an exponential random variable is. So let us assume x is a continuous random variable on the interval 0 to infinity. So it can only take positive values, it cannot take negative values. And let's assume the distribution of this random variable follows the function fx is equal to lambda e to the minus lambda x. And let's assume that lambda is just some parameter that is always positive. And we usually refer to this as a rate parameter. So lambda is some rate parameter. So if x is a random variable that satisfies this domain criterion and follows this distribution, so what does this distribution look like? So if you were to graph this, this will look like this type of thing. So almost like an exponential decay type of curve. So if x is a random variable that satisfies this criteria, then x is called an exponential random variable, whose PDF, probability density function, is this function given here. So a couple things that we should be able to ask ourselves. First off, is this a probability density function? So I haven't really told you what lambda represents, and we'll get to it eventually, but regardless of what lambda is this really always a probability density function? So that's the very first question that we need to answer. So is fx really a probability density function? So in order for it to be a probability density function, it needs to satisfy two properties. The first property is that the function must always be non-negative. So if we look at the probability density function fx of x is equal to lambda e to the minus lambda x, remember that lambda is assumed to be a positive constant. We know that exponential functions are always positive, assuming that x and lambda are both real numbers, and as long as lambda is positive, then we should be okay. So the product of two positive numbers are always going to be positive, therefore this is always above the x-axis. Now the second criteria in order for this to be a probability density function is that the area underneath this curve on the interval 0 to infinity must be equal to 1. So is that really the case, regardless of what lambda is? So if lambda is 3, is the area 1? If lambda is 1.2, is the area still 1? And if so, then we actually have a family of probability density functions, and that's actually very, very useful. So is the integral from 0 to infinity of lambda e to the minus lambda x equal to 1, regardless of what the value of lambda is? And the answer is yes. So let's just do a quick proof, just in case you do know calculus, you should be able to follow. And if you don't know calculus, then that is okay. This proof is actually quite quick. So lambda is just a constant, so that can always be factored outside of my integral sign. And I'm just left with the integral of e to the minus lambda x with respect to x. So since minus lambda is the constant by the inverse chain rule, this is going to be equal to lambda times that constant reciprocated times e to the minus lambda x. And by the fundamental theorem of calculus, we're going to evaluate that at infinity, evaluate that at 0, and then subtract. So that's all the calculus part that you really need to know. So those cancel, just leaving us with -1. And as x goes to infinity, this thing is going to go to 0. And then once I plug in 0, I'm going to get 1. So notice that -1 times -1, that's just going to be 1. Therefore, the integral underneath this function is equal to 1 for all values lambda. That's a positive real number. So therefore, this truly is a probability density function regardless of the value of lambda, assuming that lambda is, of course, a positive number. Now, one question that we have yet to ask or answer is this: what does lambda represent? So we remember from the Poisson distribution that lambda represented the expected value, so one could think, well, is lambda the expected value of an exponential random variable? And the answer is actually no. So maybe we can at least use the expected value to possibly create a meaning for lambda, and that's exactly what we would do. So we know that the expected value of a continuous random variable is going to be equal to the integral over the support of x times the density function, right? So since we're working in a exponential random variable, the support is precisely equal to the integral from 0 to infinity of x times our probability density function, right? And now if you don't know calculus, or maybe even if you do know calculus, you might not exactly know how to continue with this calculation. But if you do know calculus, then you can use integration by parts, a very familiar algebra trick, in order to evaluate that. And eventually you will get 1 over lambda. So what does that mean? So remember, expected value is the average value for the random variable, and we have this nice relationship to 1 over lambda. So that means lambda is the reciprocal of the average, right? Because if expected value is equal to 1 over lambda, that means lambda is equal to 1 over expected value. And remember, expected value and mu of x are equivalent representations, so they mean the exact same thing, just from different angles. So that's a brief theoretical introduction to the exponential distribution. Now let us look at a real-world application of where you may want to use this type of distribution, and actually how to calculate some of the probabilities and percentiles associated with it. So let us suppose that the amount of time that people spend shopping in a grocery store is exponentially distributed with an average shopping time of approximately, let's say, 45 minutes. What is the probability that a randomly selected person spends more than 1 hour shopping? So let's just look at a couple of the things that are mentioned here so that we sort of understand what we're talking about. So here we're talking about the amount of time that people spend shopping in a grocery store. So of course, since we're working with time, generally speaking, this is going to be a continuous random variable. So we need some distribution to describe that distribution of time. It's given that the time is exponentially distributed. So what does that mean? So that means if we look at the distribution of the time, that means the distribution should follow something along this type of curve. Now, which exponential distribution is it? Well, it really depends on the average shopping time, right? So it's given that the average shopping time is 45 minutes. So given this information, we should be able to figure out which value of lambda for our distribution that we want. So remember that the density function for an exponentially distributed random variable is going to be equal to lambda e to the minus lambda x. So what is lambda? Lambda is the reciprocal of the average. So that means lambda must be equal to 1 divided by 45, right? So now that we have our distribution in front of us, now we can calculate probabilities and everything else. So what is the probability that a randomly selected person spends more than 1 hour shopping? Right, so in terms of this picture, how can we find that? So what is the probability that a randomly selected person spends more than 1 hour shopping in this grocery store? So keep in mind that this distribution, x, is in minutes. So since we are in minutes, we need to make sure that this unit in terms of what we're integrating is also in minutes as well. So that means this is the same thing as the probability that x is greater than 60 minutes. So remember, greater than 60 and greater than or equal to 60 equal to the same value, even though they are different problems. So if we look at our distribution, we're just going to find 60, and we're going to find the area underneath the curve from 60 to infinity. So that's going to be equal to the integral from 60 to infinity of our probability density function, which is f. So what is that going to be? So that's going to be equal to the integral from 60 to infinity of lambda e to the minus lambda x dx. And if you're working in Desmos, you should be able to just evaluate that. That's going to be approximately equal to 0.2636, or if you know basic calculus, you should be able to figure that out as well. Now, what if we were to have asked another example? So let's assume what's the probability that we spend at most 35 minutes. So this is at most 35 minutes. This question, although different from less than 35 minutes, would give us the same exact answer from the calculus perspective. So remember, this is going to be equal to the integral from 0 to 35, because the minimum value for this random variable is 0, right? So negative infinity to 35 is the same as 0 to 35 for an exponential random variable. So we're going to be integrating our distribution from 0 to 35. So that's, again, going to be the integral from 0 to 35 of our distribution function. Right, same average. And one can find that in Desmos to be approximately equal to 0.5406. Or if you know calculus, you should be able to figure that out by yourself. Now, question. Do we need to know calculus to answer these questions? And the answer for this question, surprisingly, is no. Because this function, fx of x, is equal to e to the minus lambda x with a lambda in front, is a very basic probability density function, especially compared to a lot of the other ones that we're going to see in the near future. So maybe there's a formula that can actually calculate the area under the curve, for example, like the area under a triangle or a rectangle or a trapezoid or some shape that we're familiar with. Maybe there's a formula to easily calculate these areas, and the answer is, of course, yes, there exists one, and I'm going to give that to you. So let's assume we have an arbitrary exponential distribution, and let's assume, that's dictated by some parameter lambda. Now let's assume we want to answer this question. So what is the probability that capital X is less than or equal to little x, right? So if you remember back when we were discussing frequency distributions, this is actually the same exact format as the cumulative density function or a cumulative distribution function for a random variable or a data point, right? So this is the cumulative density function evaluated at little x, right? And sometimes, remember, we abbreviate that by capital F sub x, and we're associating that to a random variable x. So is there a cumulative density function, a nice representation for that, for the exponential random variable? And the answer is yes. So how would you find it? So the cumulative density function for a exponential random variable can be found by doing the integral from 0 to x of your probability density function, and you should be able to show via calculus that this is just going to be 1 minus e to the minus lambda x. So this is our cumulative density function. So if I were to ask you what is the probability that x is less than or equal to 35, you can actually just plug in 35 into this distribution and get the answer immediately. So that's going to be equal to 1 minus e to the minus lambda. So what was lambda for us? That was going to be 1 over 45 to the power of 35. And once you evaluate that in your calculator, that actually gives you the same exact answer, which is pretty nice. But what about the other direction? So if you have the probability that x is greater than, say, 20 minutes, so that's 1 minus the probability that x is less than or equal to 20. So that's going to be equal to 1 minus e to the minus 1 over 45 to the power of 20, right? And then we can cancel some stuff there and we can get an answer if we really want to. Now, a nice interesting thing to think about, what if we want the probability of spending anywhere between 30 and 45 minutes in the grocery store? So how can we get this very simply via cumulative density functions? So if we look at our picture for our density function, so 30 is chilling here, 40 is chilling here, and our goal is to find the area of this interior region. So notice if I were to look at the area all the way up to 45, and also look at this little baby area from 0 to 30, we can actually see a very nice picture here, right? So the probability that 30 is less than x is less than 45 is actually equal to the probability that x is less than or equal to 45 minus the probability that x is less than or equal to 30. So if we use the cumulative density function, that's precisely equal to capital F of 45 minus capital F of 30, right? So that means the integral from 30 to 45 of our original probability density function can equivalently be written in terms of the cumulative density function. And if you have taken calculus, this should look very, very familiar from the fundamental theorem of calculus that you should have learned in Calculus 1 and or Calculus 2. So there are definitely some parallels associated with those. Now let us look at a few examples on how we can use, for example, this cumulative density function, because now technically we don't need to know calculus in order to solve these problems. And let's look at how we would calculate, say, medians and percentiles using this formula. So let's assume again the same exact problem, that x is exponentially distributed with the expected value being equal to 45 minutes. So we're still talking about the shopping in a grocery store problem. What is the median shopping time for a randomly selected person? So remember what median means. So that means half of the data is to the left of the variable and half of the data is to the right of this particular value in this variable expression. So that means the integral from 0 to m of our exponential distribution must be equal to 0.5, and the integral from m to infinity of this random variable must also be equal to 0.5. Equivalently, this is the particular value m for which the cumulative density function, capital F of x, is equal to 0.5. Right? So if we were to substitute this value m into the cumulative density function, that means 50% of the data must be equal to that particular value, right? So that's pretty much what the cumulative density function represents, right? So that's 1/2 or 50%, right? So is there a cute formula that we can always calculate for an exponentially distributed random variable to calculate the median? And the answer is, of course, take a guess, yes. So how would we go about that? So remember that the cumulative density function for an exponentially distributed random variable is going to be equal to 1 minus e to the minus lambda x. So we want to find the value of x such that this is equal to 1/2, right? So what am I going to do? I'm going to subtract both sides by 1 and then negate both sides. So that's going to give me e to the minus lambda m must be equal to 0.5. And then I'm going to take the natural log of both sides of this equation, and that's going to give me negative lambda m is equal to the natural log of 1 over 2. And remember from our rules for natural logarithms, that's the same as natural log of 1 minus natural log of 2, and you should know that that is equal to 0, just leaving us with negative natural log of 2. So notice that both sides of this equation is going to have a negative sign. That means lambda times m must be equal to the natural log of 2. That means the median of an exponentially distributed random variable with parameter lambda is always equal to the natural log of 2 divided by a parameter lambda. Very cute formula for the median of an exponentially distributed random variable, which is pretty nice. So that means in continuation of our example, remember that lambda was equal to the reciprocal over average. That means this is going to be equal to the median shopping time is going to be equal to the natural log of 2 all over 1 over 45, which is going to be equal to 45 times the natural log of 2. And once you do the natural log of 2 times 45, you're going to have that's approximately equal to 31.1 minutes. So that's the median shopping time. What about percentiles? Because remember, for the continuous random variable case, the median and the 50th percentile are equivalent numbers. So let's look at percentiles briefly. So what is the 70th percentile for shopping time? So what does that mean in terms of the exponential distribution and its picture? So that means 70% of people spend at most this particular time, right? So this is the 70th percentile for which we're interested in finding, right? So one can find that this particular number, and let's assume that this is just some arbitrary value, p. So the pth percentile for an exponentially distributed random variable can actually always be found via the formula, the negative natural log of 1 minus that percentile percentage, all divided by our parameter, lambda. And using some basic, solving equations, for example, you set the cumulative density function equal to p, solve that equation for x, you're going to get this equation, which is a nice little algebra exercise in case you're interested in. But this can definitely give it to you. So therefore, the 70th percentile for shopping time is going to be equal to the negative natural log of 1 minus 0.70 all over 1 divided by 45. So what's that going to be? So that's going to be equal to negative 45, because we have a fraction on the bottom, times the natural log of 0.30. Remember, the natural log of any number between 0 and 1 is always going to be a negative number, so they're going to cancel out, and then you're going to have approximately equal to 54.2 minutes. So that means 70% of all people who shop in this grocery store usually spend at most 54.2 minutes shopping there, right? And that is how you can calculate any percentiles and also the medians of an exponentially distributed random variable. Now let us look at another distribution that's closely related to this one. Now let's suppose that x is a new random variable, but not just any random variable, but a sum of exponentially distributed random variables, each with the same rate parameter lambda. So let's just sort of break this down before I give you the rest of the definition. So x is going to be a sum of other random variables. So x1, x2, x3, all the way down to, let's call it xr. So r is going to be the number of random variables that we're going to be summing up. So x1 is going to be an exponentially distributed random variable with parameter lambda. x2 is also going to be an exponentially random variable with parameter lambda. x3 is also going to be an exponentially distributed random variable with parameter lambda. And all the way out to xr, also going to be an exponentially distributed random variable with parameter lambda. So each of these particular values is an exponentially distributed random variable with the same exact rate parameters. Now, one can ask, well, what happens when each of these random variables have different rate parameters, like lambda 1, lambda 2, lambda 3, down to lambda r? Of course, yes, you could do that, but the distribution does get a little bit more complex, right? So we always start with the most easiest case. So what's the purpose of this? Well, x1 could be one person that's shopping in the grocery store, x2 is another person that's shopping in a grocery store, x3 is another person that's shopping in a grocery store, and so on, right? So if you want to ask, well, what's the probability that the total amount of time that 10 people shopping in a grocery store is more than 3 hours? What's the probability that, that is the case, right? So if that is the case, then that means x would help describe that distribution of total time that people spend in the grocery store. So one can ask, well, if x1 down to xr are all exponentially distributed random variables, well, what type of distribution will x have? Will it also have an exponential distribution? The answer is no. So the name of its distribution is actually called a gamma distribution. So a gamma distribution is going to help model the sum of independent a sum of independent exponential random variables whose rate parameters are all equal to one another. So how many exponential random variables are we going to have? We're going to have r of them. And what's the rate parameters for each of them? We're going to call them lambda. Okay? So what does the distribution for a gamma distribution look like? So that's going to be equal to fx of x is going to be equal to lambda to the power of r all over gamma of r times x to the r minus 1 e to the minus lambda x. Here, x must be a positive number, and the number of exponential random variables also must be a positive number as well. So that is the gamma distribution in its principal form. So let's just break down again what these elements mean. So r is the number of exponential random variables we're dealing with. And lambda is the rate parameter associated to each of those random variables. Now what's this interesting function? Maybe you've seen this, maybe you have not. So this is another function. So the gamma function of r is going to be equal to the integral from 0 to infinity of t to the power r minus 1 e to the minus t dt. So this is a special function that's usually introduced in calculus 2. But sometimes you actually don't need to use the integral representation for this function, because if r is a natural number, like 1, 2, 3, 4, and so on, then gamma of r actually is equal to just r minus 1 factorial. So that means, for example, gamma of 5 is the same as 4 factorial, which is the same as 24. So as long as the value of r is very nice, you actually don't need to know calculus to evaluate this particular function, which is actually pretty nice. So if r is a natural number, then the density function for a gamma distribution actually doesn't even have gamma in it at all then, right? That's going to just be gamma lambda to the power of r minus 1 factorial, x to the r minus 1, e to the minus lambda x. Now, if you are using Desmos to calculate probabilities, you can actually use this explicitly, and it will extrapolate r minus 1 factorial with respect to gamma by its default. So you can actually avoid this definition of gamma in Desmos if you're calculating probabilities there, and just use this factorial representation on its own, and you will get all of the answers that you want. So if this is the case, well, how do we use it and how do we interpret it? So remember, if r is equal to 1, so if we only have one exponential random variable, then this is going to be an exponential PDF, right? But if, of course, if r is greater than 1, then you should be using the gamma probability density function. Since this is a random variable, of course, it has an expected value and a variance formula. So the expected value of a gamma random variable is going to be r divided by lambda, and the variance of a gamma random variable is going to be r over lambda squared. Now, why is this? Well, you can prove these formulas via the calculus, but you actually have seen a similar distribution like this in the discrete world. So do you remember which distributions are sort of related to each other in this regard? So these have a similar connection to geometric and the negative binomial random variables from the discrete world, right? Because remember, for geometric random variables, we try something until we get our first success, and negative binomial is we try something until we get our successes. And if you remember the formulas for the exponential, the geometric and the negative binomial, they practically have the same exact representations or the same exact connections, if you may, with each other, which is actually pretty interesting, right? But there are definitely some parallels between each other and how they sort of derive each other. But that's just the theoretical introduction to the gamma distribution. So now let us take a look at an application for which you may want to use the gamma distribution for. So let us suppose you are on a team of 7 people that is competing in a trivia relay, where the average amount of time each team member spends on each question is exponentially distributed with an average response time of 4.72 seconds. So let's just assume a couple things here so that we can use the things we've been introduced to answer these questions, right? So first off, we're on a team of 7 people and we're competing in a trivia relay. So one person answers a question, and then the next person answers a question after the first person is done, and then this process repeats for a series of rounds, let's assume. So the average amount of time that each team member spends is exponentially distributed with the average response time of 4.72, right? So if each of these random variables, for example, x1, x2, all the way down to x7, so that's our entire team, so we're assuming that each of them are exponentially distributed with an expected value of 4.72, that means the lambda value for each of these random variables is going to be 1 divided by 4.72 for each of them, right? So lambda 1, lambda 2, lambda 3, all the way down to lambda 7 is 1 divided by 4.72. So usually we just call that lambda. So what is the probability that it takes more than 30 seconds for your team to finish one round of the trivia relay, right? So just, one sequence of 1 through 7. So what are we actually looking at here? So we're going to define t to be the total time to be equal to the sum of the times that each of the members on the team takes to answer these questions, right? So again, each of these are exponentially distributed. Let us just assume that these are independent times. So me taking longer on a question is not going to affect the time that it takes you to answer the next question or so on. So let's assume independence just for the sake of conversation. And each of them have, at least for this conversation, the approximate average amount of time for response times, right? Realistically, this is not the case, but let's just assume it just for at least an approximation for what we want. So since each of these are exponentially random variables, that means this is going to follow a gamma distribution. So this is going to be a gamma random variable. What's the value of r? So r is going to be equal to 7. That's going to be how many exponential random variables we are adding up. Now keep in mind this does not need to be a natural number, right? And there's several applications that you can sort of consider or think about where that might not be the case, right? So what is our probability density function for our application going to be? So the gamma distribution for this is going to be equal to lambda 1 over 4.72 to the power of r all over of gamma r, and then x to the r minus 1 times e to the minus 1 over 4.72, so that's lambda x. And if this is the case, then the probability that this random variable, I think I used t before, so let's just change that to t. All right, so that's our total amount of time. So the probability that this is greater than 30 is going to be equal to the integral from 30 to infinity of this density function that I've defined just above. And you can show that that's approximately equal to 0.5493. Now, is there a nice distribution or a nice cumulative density function for the gamma distribution? I'm not going to answer that question here, but maybe you want to try and find it if you do know a little bit of calculus. So that is just some of the basics associated to the gamma distribution, and how you can solve some problems like that, how you would find percentiles and medians and other various types of problems. Of course, that follows the same exact strategy as we have already done before with the generic case of random variables. Anyway, so those are two new distributions, gamma and exponential. In the upcoming videos, we're going to introduce a couple more special PDFs that are oftenly seen in applications. I hope to see you there. Take care.